Welcome back. Problem 11-14. So statement is select the lightest weight steel wide flange beam from Appendix B that will safely support the loading shown. The allowable bending stress is 24 kSi and allowable shearing stress is 14 kSi. So you can see this is the beam having a roller support at this end and pin support at this end. And there is a load which we will distribute into a uniformly distributed load and then uniformly increasing load. Clear? All the values of the loads are given. So what we have to find, we have to select the lightest weight flange beam that can simply support the load. So let's start with the solution. So first step is that if you remove this roller support, so you will be having a reaction force which is equal to R1. Clear? And if let this point is 1, so and if you remove this support at this point, so at this point is 2, so you will be having a reaction force which is R2. So we will draw the free body diagram of this beam. Clear? So this is reaction force which is equal to R1. Clear? And this is equal to R2. Now you can see that there is a load here. The magnitude of load is 10. So if I take it a horizontal uniformly distributed load, so and I will draw it over here or by using a dotted line. So this uniformly distributed load having magnitude 10 kips per feet. The total length of the beam is equal to 12 feet. Clear? So this is 12 feet. And if I take the half, so this will be equal to 6 feet and this is also equal to 6 feet. So when this distributed load will be converted into point load, so it will be 6 into total length of the 10 into total length, which is equal to 12. Not 6 but 12, because 6 plus 6 is 12, and that will be equal to 120 kip per 120 kips, because we have multiplied with length. Now you can see you have a triangular load, a uniformly increasing load from this till 6 length. So if I draw it by using a triangular dotted line, so it will be like this. Here the magnitude is 5 because 10 minus 5, so here it will be equal to 5. So this will be equal to 5 kips per feet. Okay. Now when we convert this uniformly increasing load into a point load, so it will, since this is a triangular area, so it will be equal to 1/2 into 5 into its length, which is 6, and that will be equal to 15 kips. 6, 5, 30, 30 divided by 2. And what will be its location from this denser side, from this side? So it will be L by 3. So 6 by 3 is 2 feet. So this will be 2 feet. Same is the case, you can see then you have uniformly decreasing load of the same magnitude. So it will be again the same. If when converted into point, it will be equal to 1/2 5 times 6, which is equal to 15, and that will be acting at a distance of 2 feet from this denser side. Now we'll apply equilibrium condition in order to find this R1 and R2. So first equilibrium condition is that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about this point 1, the first moment is this one, which is 15 into perpendicular distance. This remaining distance is 4 feet. So, and this is producing clockwise, so it will be negative. So I will write 15 into 4, and that is clockwise negative. The second moment will be this 120 kips and perpendicular distance is 6 feet, and this is also clockwise, so it will be negative. So minus 120 into 6. The third moment that is produced due to this 15 kips force, and now perpendicular distance is 8 because 6 plus 2 is 8, and this is also negative because this is producing clockwise. Minus 15 into 8. The last force which producing moment about point 1 is, this is your point 1 and this is R2 into 12, and this is producing counterclockwise, so it will be positive. So I will write plus 12 RA is equal to 0. Okay, so here you will get minus 60 minus 720 minus 120 plus 12 RA is equal to 0. So when you add all this, 720 plus 120 is 840 minus 60, which is minus 900, plus 12 RA is equal to 0. So RA will be 12 RA is equal to 900. So RA will be equal to 900 divided by 12, which is equal to, RA is equal to 75 kips. 75 kip. Now you have this RA, you can find RB as well by using sum of all forces along y direction must be equal to 0 and force upward taken as positive. So R1, sorry, this is not RA, this is R2. Sometimes this happens, this is R2. So this is R2, this is R2. Okay, now you have R1 minus 15 minus 120 minus 15 plus 75 is equal to 0. Okay, so you have R1, this will give you minus 150 plus 75 is equal to 0. So R1 will also equal to 75 kip, not R5, R1. Now you have R1 and R2. So what we will do is that we will cut the beam over here in order to find the shear force and bending moment for this. So for that I will draw the free body diagram of half of the beam. So if this is the half of the beam where you have R1 over here, which is 75, and we have a uniformly distributed load till this length, the uniformly distributed load is 10 kip per feet, and then there is a 5 kips per feet. The length is, total length, half of this length is 6 feet. So when you cut it, so you will be having a shear force V and you will be having a moment. Let this is your point 1. So you will be having V1 and M1. So when you convert this uniformly distributed load into a point load, so you have to multiply this 10 with the length, which is equal to 60 kips. 60 kip. And when you convert this uniformly increasing load, this one, into a point load, so you will be having this load will be equal to, I will write it over here, this will be equal to 1 over 2 5 multiplied by 6, which is equal to 15. Okay, 15 kips, and that will act at a distance of L by 3. So L is 6, so 6 by 3 is equal to 2 feet. Okay, and this uniformly distributed load will act at a half of this total length, which is 3 feet. Now apply equilibrium condition in order to get this V1 and M1. So first equilibrium condition is that sum of all forces along y direction must be equal to 0 and force upward taken as positive. So you can see 75 minus 60 minus this 15 minus V is equal to 0. So I will write it 75 minus 60 minus 15 minus V is equal to 0. So 75 minus 75 is equal to V. So V is equal to 0. So it means that at the mid of the beam, shear force is 0. Now we will find moment. So sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, first moment is R 75 into 6 and that is producing clockwise, so it will be negative. So I will write minus 75 into 1. The second moment will be due to this 60 into perpendicular distance is 3 and this is producing counterclockwise, so it will be positive. So plus 60 into 3. The third moment will be due to this load and this load is 15 into 2 and this is also producing counterclockwise, so it will be positive. So I will write plus 15 into 2 and the last external moment is M1 or M1 is equal to 0. So when you solve this, you will get this moment will be equal to 75 into this distance is 6, not 1. 75 into 6, so it will be equal to 450 minus 180 minus 30. So moment M1 will be equal to 240 kips into feet. Now you have this moment at the mid, so we will draw the shear force and bending moment diagram. So for that I have to draw vertical lines from the end of the beam. We have taken half of the portion and we will use the advantage of symmetry to get the shear force and bending moment diagram. So here X in feet, clear. You will having moment as well. Shear force. Here you will draw its bending moment X in feet. You will have moment which will be kips into feet. Here you will be having unit of shear force is kip. Now we will decide, we will take the scale, let one division is equal to 50. So this is 50 kips, this is 100 kips. Minus 50 minus 100. Okay, so at first point we have R1 which is equal to 75. So 75 will be in the mid. So this is your 75. And at the mid of the beam you have shear force is equal to 0 because we have calculated this over here. Shear force will be 0 at the mid. And you can see that this shear force, this load is uniformly increasing. So bending shear force will be 1 degree higher and it will be 2nd degree. And since this load is downward, clear, so you can see this load is downward. So the slope of shear force will be 2nd degree curve and it will be decreasing. Okay, now you can see the same thing here. The shear force will now increase and at this end you will get 75. So this line will continue over here. So it will be in 75, minus 75. And at the end you have R2 is plus 75. So it will bring it to 0. So this is your shear force diagram. Now we'll move toward bending moment. So we will take this as 100. This is 200 kilonewton into feet 300. So at point first we have R1, at R point 1 we have moment is equal to 0 because X is equal to 0. And at the mid of this we have maximum bending moment because shear force here is 0. So 240 kips. So at mid we will be having 240. So 240 will be like this. Now you can see that shear force is a 2nd degree line. So bending moment will be 1 degree higher and it will be third degree and slope will be increasing. And then at the same, using symmetry, it will go down. It will go down. So this is your bending moment diagram. So here it is, moment is 240. Now what will be the next step? So we will take from BMD, bending moment diagram. Maximum bending, absolute value of bending moment is 240 kips into feet. So when you convert it into inch, so 240 multiplied by 12, and the unit will be kips into inch. That is maximum bending moment. Now we know that maximum bending stress is equal to, or allowable bending stress is equal to maximum bending moment into C divided by I. So it will be equal to maximum bending moment into I divided by C, and I divided by C will be the required section modulus. So we will find this required section modulus. So required section modulus is equal to maximum bending moment divided by maximum or allowable bending stress. So maximum or allowable bending stress is also available, and maximum moment is also available. So maximum moment is 240 into 12 divided by allowable bending stress is 24 KSI. So 24. So when you calculate it, you will get required section modulus will be equal to 120 inch power cubic inch. So this is required section modulus. Now we will go to Appendix B, and we will check the required section modulus that is near to 120 and the lightest wide flange beam. So I will move toward this. So you have to go to the end of the book, Appendix B, wide flange beam. So we will check from the start. So what we will do is that, let me select the pen. What's the problem? Okay, so we will select this blue pen. So you can see 120 was the value. So here this is S, so you have to go downward. So the value which is above 120 is 131, 154. Clear? As well as you can see this is 131 and 154. So these two values are closer to 140. So we will check it. This is 68, this is 62. And here you can see that in somewhere it was written, okay, this is its, the second value is, where is the table? It is here, okay. So the second value is pound per feet, its weight pound per feet. So 68 is greater, so we will select this wide flange beam. We will also note down its depth as well as its thickness of web. N is SX, which is 131. So note down this value and we'll back to the problem. So we, from appendix, we get W24 by 62. Clear? Having its SX section modulus as 131 inch cubic inch. Depth of this beam is 23.74 inch, and thickness of its web is 0.430 inch. So we have selected this beam. This is the required beam, but we will check it with the shear. So check shear stress. We know that maximum shear stress is equal to maximum shear force divided by area of web. So maximum shear stress force is 75 from SF the shear force diagram. So 75 divided by area of web is depth, which is 23.74, into thickness, which is 0.430. So when you calculate it, it will be 7.35 KSI. Now you can see this maximum shearing stress, which is equal to 7.35 KSI. We will check it with the allowable shearing stress. So allowable shearing stress is 14 KSI. So this is less than allowable shearing stress, which is 14 KSI. So hence the conclusion is that W24 by 62 is required wide flange lightest steel beam, and that is your answer. And this was all about this problem 11-14. I hope you have learned this video and you have enjoyed it as well. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Also provide me feedbacks about my video. Thank you for watching.